Hello, students. Welcome. In today's session, we're going to tackle a really important topic from your digital electronics syllabus, basic sequential circuits. Now, I want you to pay close attention, okay? Because getting these concepts right is absolutely crucial, not just for your university exams, but really for understanding how almost every digital device you use actually works. All right, let's start with a big question. So far, we've looked at circuits where the output depends only on the input right now. But think about this for a second. How does a calculator remember the first number when you press the plus key? Or how does any system remember what happened just a moment ago? Well, this very question, how a circuit can remember the past, is the key difference between simple combinational logic and what we're talking about today, sequential circuits. These are the real heart of computer memory. So the answer, as you've probably guessed, lies in these special circuits called sequential circuits. And, to really understand them properly, the best way is to compare them with the circuits you already know pretty well, the combinational circuits. Okay, take a look at this table. It gives us a direct comparison, and I really want you to focus on the key differences here. With a combinational circuit, it's simple. The output depends only on the inputs you give it right now. It has absolutely no memory. But for a sequential circuit, things are different. The output depends on the present inputs and the past history of inputs, which we call the circuit's state. And for that to happen, it must have a memory unit. Now, this does make them a bit slower and harder to design, but that memory is exactly what makes them so powerful. By the way, this comparison is a very common exam question, so please make sure you understand this table inside and out. Now, this diagram shows you exactly how it works. Look at the fundamental structure here. Do you see that critical feature? The feedback loop. This is the whole secret. The output isn't just sent out. Part of it is stored in a memory element. And this stored value, we call it the internal state, is then fed back as an input. That's it. That is the physical mechanism that lets the circuit remember its past. So the next output will depend on the new external inputs plus this stored internal state. All right, so the circuit has memory. We've got that. But this brings up another question, right? How do we control when the memory gets updated? We can't just let it change randomly. That would be chaos. The whole system needs a signal to keep everything in sync. And that signal, well, we call it the clock. And here it is. You can literally think of this clock signal as the system's heartbeat. It's just a continuous, oscillating square wave, going up, then down, up, then down. Now for what we need, the most important parts of the transitions. See that jump from low to high voltage? That's the rising edge. And the drop from high to low? That's the falling edge. We're going to see that these exact moments are what we use as triggers to make the memory elements update. This idea of a clock signal leads us straight to the most common type of sequential circuit you'll ever study, the synchronous sequential circuit. And the name really says it all. Everything happens in sync with the clock. All the memory elements, all across the entire circuit, change their state at the exact same instant, right when that clock trigger happens. It's this synchronous operation that keeps everything stable and predictable.
Okay, this is a very important point. It's how the memory elements actually listen to the clock. You see, the simpler elements, which we call latches, are level triggered. That means they're paying attention to the input for the entire time the clock is high or low. Now, this can be a problem, right? Because the inputs might change a few times during that period, and you don't know what the final state will be. So to fix this, we use more advanced elements called flip-flops. These are edge-triggered. They only change their state at one precise moment, that instant when the clock has a rising or a falling edge. It's this precision that makes our big, reliable digital systems actually possible.
Okay, so let's zoom in a bit. Let's study this fundamental 1-bit memory element in more detail. This element is the flip-flop, and it truly is the basic building block for pretty much all sequential logic. Now, in your course, you'll come across several types of flip-flops. There's the SR, the D, the T, and the JK flip-flop. For our discussion today, we're going to focus on the JK flip-flop. And why is that? Well, it's because it's considered the most versatile of them all. You can actually make it behave like any of the other types. So, this table you see here, this is the characteristic table for a JK flip-flop. It tells you everything it can do. Let's just walk through it. If both J and K are 0, the next state, Q sub next, is just Q. It holds its value. We call this the hold or memory state. Simple enough? Now, if J is 0 and K is 1, the flip-flop resets. The output goes to 0. If J is 1 and K is 0, it sets, and the output goes to 1. And finally, and this part is unique to the JK flip-flop, if both J and K are 1, the output toggles. That means it just flips to whatever the opposite of its current state is.
Q prime. Okay, now we're getting to a topic that is an absolute favorite for university examiners: flip-flop conversion. You will very, very often get a question asking you to convert one type of flip-flop into another. Like converting an SR into a JK or a JK into a D-type. So let's walk through a standard example together so you can master this procedure.
So in this section, we're going to tackle a specific problem: converting a basic SR flip-flop into the more versatile JK flip-flop. This is a really practical skill, and the method we're about to use, it works for all flip-flop conversions. So let's begin.
The great thing is, the conversion process is very systematic. It always follows these 3 steps. First, step 1, you create something called an excitation table. Then, step 2, you use that table to figure out the Boolean expressions you need, usually with K-maps. And finally, step 3, you draw the final logic circuit from those expressions. Please remember these 3 steps. They are your guide for any conversion problem. Okay, here's step 1, making the excitation table. Look on the left side. We list every possible combination of our target inputs J and K and the present state, which we call Qn. Then, for each row, we write down what the next state, Qn plus 1, should be. We get that right from the JK flip-flop's own characteristic table. Now for the tricky part. For the last 2 columns, we have to ask ourselves, to get from Qn to Qn plus 1, what inputs S and R do I need to give to the SR flip-flop that I have? We fill those in using the SR flip-flop's excitation table.
And now, step 2. We take that excitation table we just made, and from it, we derive the logic expressions for S and R, and the best tool for that is, of course, the Carnot map. So we make one K-map for the S output, using J, K, and Qn as our inputs. As you can see, after we group the ones, we get a simple expression, S equals J and Qn prime. We do the exact same thing for the R output, with its own K-map. That one simplifies to R equals K and Qn. And there we have it. Those are the 2 key equations we need for our final circuit.
And here is the final step. Step 3, the circuit diagram. We start with our basic SR flip-flop. Now we just need to add logic to implement our 2 equations. Let's see. For the S input, the equation was S equals J and Qn prime. So we grab an AND gate, we connect the external J input and the Qn prime output from the flip-flop to this AND gate. And the output of that gate? That goes right into the S input. Simple. For the R input, the equation was R equals K and Qn. So we get another AND gate, connect the external K input and the Qn output to it. And that's it. We're done. This whole thing now works exactly like a JK flip-flop.
So, okay, we've seen how a single flip-flop can store just one bit of information. But the real power, the real magic, happens when we start connecting several of them together. Imagine connecting, say, 4 flip-flops in a group. Now we can store a 4-bit number. And a group of flip-flops like this has a special name. We call it a register.
Now, one of the most important applications of registers is something called a shift register. And the name tells you exactly what it does. Its job isn't just to store data, but also to shift it, to move the data from one flip-flop to the next, 1 bit at a time with every tick of the clock. This is absolutely fundamental for things like converting data from serial to parallel, which you need all the time in data communication. And of course, there are different types depending on how you put the data in and take it out, like serial in, serial out, or maybe serial in, parallel out, and so on.
Okay, let's just zoom out for a minute and think about the big picture. We've gone through a lot of theory, but why does any of this matter? Why are sequential circuits so important in the real world? Well, the truth is, sequential circuits are the absolute foundation of all modern digital systems. Those registers we just talked about, they're sitting right inside your computer's CPU, holding data for calculations. Huge collections of flip-flops, well, that's what all computer memory is made of, from the RAM in your laptop to the super fast cache inside the processor. And these complex sequential circuits called state machines, they are the controllers, the brains that manage the entire sequence of operations. Without these things, computation as we know it today just wouldn't be possible.
So look, if you remember only one single thing from this entire session, let it be this sentence. This is the defining property. Unlike a simple logic gate, a sequential circuit's output depends on the past history of its inputs. It's this one ability, the ability to remember, that lets it perform all the complex, time-based operations that we rely on every single day. And this, of course, leads us to the next level of your studies. Think about it. What happens when you have millions of these flip-flops all working together, all synchronized to a clock that's ticking billions of times a second? Well, new practical challenges start to appear. You'll have to learn about really important timing concepts like setup time, hold time, and clock skew to make sure your high-speed designs actually work. But that is a fascinating and advanced topic for another session. Thank you.